All right, so Niels Bohr was one of the next scientists to come along and kind of use what had already been some of the theories that had come along with Einstein and Planck. So again, classic physics let us down and couldn't explain some of the atomic theories of the day. So Niels Bohr, like I said, starting using the work of Einstein and Planck, applied the theory or used their ideas and applied his new theory to the simplest atom. So he started out just by looking at hydrogen. And of course, hydrogen has one proton and one electron. So it's very simple. We're only looking at one electron, which is sort of, he came up with all his ideas using the one electron. So what he used was something called line spectra of atoms, and he explained what was going on with these line spectrum. So before we look at Bohr's theory, let's talk about what a line spectra is. Okay, so if you take white light, so white light we know has all of our different wavelengths, and as I'm sure you all know, if you put it through a prism, you get all the colors of it splits it out by wavelength. And so the longer the wavelength, the less it bends, the shorter the wavelength, the more it bends. And so that's why we have all our wavelengths, and white light gives us the whole rainbow. What if instead we had some other kind of light source? In this case, this is just a tube filled with one element, in this case, hydrogen. So if you have, say, hydrogen gas filling this tube, and you heat it up, so it's giving off light, and if you take that light, so it's not white light anymore, but again, if you take that light and you feed it through a prism, instead of getting all the colors of the rainbow, all we end up with are a couple of lines. So you can see here purple, green, yellow, and red. So this is called a line spectrum because you only get certain lines of energy coming through, or certain wavelengths coming through the prism. So what that means is that this light that's coming off the gas is only made up of certain wavelengths, not all the wavelengths the way white light does. So this, of course, here at the top is our complete spectrum, the visible spectrum of white light with all the colors. And then here are some elements. So if we took sodium gas and heated it up, this is what the line spectrum would look like. A lot of yellow. Actually, sodium, when it burns bright yellow, and so that's a lot of it comes from this yellow right here. Hydrogen actually has 4 lines. So that last one must not have been hydrogen. It must have been a particular, just some gas that was anonymous. But hydrogen ends up with 4 lines in the visible spectrum. Calcium, you can see, has about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, about, more lines. This yellow one's kind of thicker. So calcium has a bunch of lines. Mercury has a bunch of lines. But like I said, Bohr focused on hydrogen and these 4 lines in particular. But the idea is, again, that when these elements are heated up and their gas is giving off light, that light does not contain the complete spectrum, only certain wavelengths. So scientist J.J. Balmer looked at those four lines in the visible spectrum of hydrogen. And again, there was like a violet, purple, blue, and red line. And so he looked at the wavelengths of those specific 4 lines and tried to figure out a way that they were related to each other. So this is not an equation you need to remember. We're going to use a variation of it, but this is just to show you what he went through, and he tried all this math to figure out, and of course in 1885 he didn't have computers or calculators or anything. He went through all this math to figure out how those 4 wavelengths, so they're like again, like I said, there was violet, purple, kind of weird to see the words in different colors, blue, and then red. So there were the 4 lines of particular wavelengths, and he did this math to figure out how the wavelengths of these 4 lines were related to each other, and he came up with this kind of weird relationship. He said, okay, the inverse of the wavelength is equal to this number times this quantity, where I took 1 over 2 squared minus 1 over n squared, where n is just some constant, like it could, so n could be, well, it couldn't be 2 because that would end up being 0, but n could be 3, it could be 4, it could be 5, etc. So again, don't remember this equation for now. We'll come up with a better one. But he did happen to find a relationship, and these and this is it. So for example, if you put 3 into this, in for n, you end up getting the wavelength for the 1 over the wavelength. So if once you inverse it, you get the red line. If you put 4 in, you get the blue line. If you put 5 in, you get the purple line. And if you put 6 in, you get the violet line. And 2 stays the same for all of them. Anyway, right, so again, this equation was only used for the hydrogen atom, and that's the only one we're going to use it for. We're going to discuss in this way. But again, if n changed to different integers, 3, 4, 5, 6, the wavelength that we got exactly matched those 4 lines. So that's very interesting. Again, here's the 4 lines. So this one's at about, what is that, about 408 nanometers. This one's at about 432 nanometers. This one's at about 484 nanometers. What did I say? This one was like 408. This one was at 432. A little bit maybe, and then this one's up here at 655. Looks like. Wait, 650, 60, yeah, 660. Okay, so these are the 4 wavelengths that when you plugged in to that equation, 3, 4, 5, 6, you would end up with these wavelengths. So Bohr used this idea to further his idea. So again, the classic description of the atom says that it should have a tiny, dense nuclei, and all the electrons, which are even tinier, are moving about the nucleus. But we still don't know how those electrons were moving. Classical mechanics thought that electrons were just kind of orbiting around the nucleus, sort of like the Earth orbits the sun, or the moon orbits the Earth, or whatever. And so classical mechanics broke down again when things got to the electron level. So, like I said, the emission spectra for hydrogen was eventually explained by Niels Bohr in 1913, and this was sort of the birth of quantum mechanics, which is, classical mechanics still works at the like our level of like everyday things, but when you get down to tiny particles like atoms and electrons, classical mechanics breaks down and we go into quantum mechanics. So here's what Bohr said. Bohr said, all right, I'm going to set down some postulates, and they are going to explain why the hydrogen atom is stable and how it gives rise to the line spectrum of the atom. So why those 4 lines are the only ones that are visible. Okay, so his first postulate was the energy level postulate. In other words, an electron can only have specific energy levels in an atom. So they, again, so stair steps versus a ramp. So electrons can only exist at different levels. So if we think of here's the nucleus down here, and electrons exist at levels that are outside. So if we're thinking this is the nucleus, actually, rings all around the nucleus, but there's different levels, and electrons can only exist at these levels. They can't exist somewhere in between. So these levels are just given values of n. 1 is the first level, it's the second level, it's the third level, it's the fourth level. So electrons can only exist at those levels. So here's a picture of those. And we'll talk about this number in a little while, the RH, in just a second. But anyway, what this is just saying is that, again, and you think of the nucleus as being down below. So these are coming out from the nucleus. The nucleus is way at the bottom below n equals 1. So n equals 1 is the first level electrons can exist on. The second level electrons can exist. The third level, they do start to get closer and closer together. The fourth level, fifth level, etc. Eventually we get to n equals infinity. N equals infinity means that the electron is no longer part of that atom and it's been stripped from the atom. And then what this green here is showing is a transition. So the electrons, like I said, they can't exist in the middle here or anywhere they want to exist, but they can exist let me find my pen. They can exist, nope, not there. They can exist down here on that level. They can exist on the second level, on the third level. They can exist, and they can transfer from one to another. So if I have an electron on the fourth level, and then it jumps down to the second level, that's allowed because it's allowed to be on these two levels. And so there's a particular amount of energy that's related to that jump. And here's a different energy. To go from 3 to 2 is a different energy. To go from, what is that, 6 down to 5 is that much energy, and so forth. Or if we go down from 2 to 1, where is it? There we go. Of course, that's a huge amount of energy. So these are, this is Bohr's first postulate, is that electrons can only exist at energy levels. These numbers will come in just a minute because they're constants that come from that equation that we saw earlier. Let's erase these because obviously electrons can't exist in the middle. They can only exist at particular levels. I'll try to, and then we can have transitions. Oh, and by the way, so notice that energy is increasing going up. So if you want to take an electron from the first level up to the second level, you have to put energy in to bring it up. But if an electron is starting at the second level and coming down to the first level, it's going to give off energy. So energy will be given out of the atom, or from the electron given out. So up is increasing energy. You have to put energy in to jump up to a higher level. And when you come down from a high level to a low level, you give off energy. I think that may be on the next few slides, but okay. So Bohr's second postulate is that, so he's telling us how these energies, what are these energy levels? So like we just saw on if n equals 1, well, this is the equation. So the energy is negative RH over n squared, where n squared are just these integers, right? If n becomes infinity, then that means energy is 0 because it's being taken away from the atom totally. So it's kind of interesting that the negative sign, so we're getting less and less negative as we go up. So down at the bottom of the page, it's more negative, and then as n gets bigger and bigger, this number gets smaller and smaller, and so it becomes less and less negative. Eventually, you get to where the electron's being removed and the energy is 0. So anyway, and RH then again is another constant. It's called the Rydberg constant, and it is, you can use it in other values, but when we're talking joules, the value of RH is 2.179 times 10 to the minus 18 joules. So the energy levels are, so for the first level, then it will just be negative 2.179 times 10 to the minus 18th. For the second level, it would be 2.179 times 10 to the minus 18th divided by 4, 2 squared. And so you can see that that the numbers are getting smaller and smaller, but they're really getting bigger because they're getting less negative. So just keep that in mind. I think we'll we'll look at that again in a minute. Again, so Bohr's postulates. Energy levels are for all integers, n equals 1, 2, 3, 4, 5, etc. And like I just said, the more negative the energy, the lower the level, the more stable the atom will be. So if the electrons, the lower they can be, the more stable that atom is. So the energy level where n equals 1 is the lowest energy level. As n increases, the value of the energy of each level becomes less negative. Therefore, energy is increasing as you go up. Even though the number is getting smaller, it's still negative, so it keeps getting, the numbers are getting bigger. N equals infinity again means the electron has been totally removed from the atom and energy then is 0. Okay, so Bohr's second postulate, which I kind of described a minute ago also, is that transitions can occur only between energy levels. So an electron can change energy levels by undergoing a transition from one energy to another. So if it goes from a low level to a high level, energy has to be absorbed. That's this one. If we're going up, energy is absorbed. And if we start at a high level and go down to a low level, energy is emitted. And it's emitted as a photon. So there's that particle duality of light. So we're talking about light as a particle right now. So it's absorbed and it's emitted if it's coming down. So yeah, so I think if you look, I should have showed that one again. Like, so again, if we put in RH, we can see that n equals 1 is negative RH. N equals 2 would be negative RH over 4. This one is negative RH over 9, 3 squared, negative RH over 16. So that's why these are getting closer and closer, because this number's getting bigger and bigger, but not proportional. So anyway, so here's the interesting thing. So it turns out if you take an electron that's in the third level and it drops down to the second level, it gives off energy with a wavelength that is red, or what was that, 600 and some nanometers. If an electron jumps from the fourth level down to the second level, it gives off light that is green. If you go from the fourth level, and if you remember that last equation that we used a couple slides ago, it was that weird number, and then it had a transition from either 3 to 2. Oh, it had this little thing. It said 2 squared minus 1 over n squared. And we said that if we plugged in 3, it would give the red light. If we plugged in 4, it would give the green light. If we put in 5, it would give the blue. And if we put in 6, it would give the violet. Well, and now we're seeing that these are just the levels. And the ones that actually go to the second level, which is 2 squared, give those colors that are in the visible range. You can also have transitions to other levels. So if you look here, you can have a transition from 2 to 1, from 3 to 1. These give off energy in the ultraviolet, so that's why they're not visible on the spectrum, but they can be detected in other ways. And if the energy transitions are ending up in the second level, those all happen to be in the infrared. So that's why we couldn't see them. But it's interesting that the 4 visible lines are all going to the second level. And so you'll see that that's why that equation had that weird thing in it, and we're gonna kind of modify our equation. So we can actually find out what that transition is, or what the actual energy is for any transition. So again, if an electron goes from a higher level to a lower one, the energy is emitted. Of course, if you go from a lower level to a higher level, it's absorbed. But either way, you can find the delta E. The delta E is just, of course, the energy of the final state minus the energy of the initial state. And we know that energy equals h nu, E equals h nu from our previous. So the energy of that transition is equal to h times the wavelength. And of course, we also know wavelength is, since lambda nu equals c, so if you plug in c over lambda in place of nu, then we know energy equals hc over lambda. So all of these things are true, and we know the energy of each level, because we just saw that. So like it's always it's negative RH over n squared. So it's that constant divided by n squared. So whatever level we're on, we can find that energy. So the energy of the final, the final energy is negative RH over whatever level, the final level it was on, n squared, and negative RH over whatever level it started from. So if we plug this into this equation, EF minus EI, and just rearrange it and simplify it a little bit, we get this following equation, which looks very much like that one that Palmer came up with. He just didn't know what he had found, and now we just can we can use that RH number instead. And so again, the change in energy equal to h nu, and the delta E is just negative RH, which is that constant. I can't remember it off the top of my head. And then in the quantity, 1 over n squared of wherever we end up, whichever level we end up, and minus 1 over. Do be careful with your fractions. You have to do that division first, do that division, and then subtract the numbers. 1 over n initial squared. So let's say it goes from the third level to the second level. The initial n would be 3, the final n would be 2, and we would just solve this for the energy. And then once we know the energy, we could also find the frequency. And we could find the wavelength as well. So I think let's do an example. We'll do that in a minute. So Bohr's theory explains not only the emission of light, but also the absorption of light. So like I said, if an electron falls from 3 down to 2, that delta E will have a value, and once you solve the value, once you solve it all and solve for wavelength, it's 656 nanometers, it's emitted, because delta E is negative, because what do you have? You have 1 over 4 minus 1 over 9. So that number is a positive number. We have, what is it? Negative RH. So 1/4 minus 1/9, since 1/9 is a smaller number than 1/4, this is a positive number, and so overall delta E is negative. Now, what if the electron goes the other way from 2 to 3? Well, what happens is this whole thing switches, and we'll have negative, oh, that's E, not H, delta E. We'll have negative RH 1 over 9 minus 1 over 4. So you can see that's the same quantity. The only thing is now this will be negative. Negative times a negative will be positive. And so your delta E will be the exact same number, but it will be positive, and that will show an absorption. And it will have the same, it will be the same wavelength and the same energy and the same frequency. It will just all be absorbed rather than emitted. So you get the same value. So you just have to remember which one you're starting from. Initial, it's always final minus initial. So if it's going from 2 to 3, then this number is negative. I think I do an example next. Maybe not, in a minute. Okay, so again, here's my energy levels, and here are the transitions. So if we go from 1 to 2, 1 to 3, 1 to 4, etc., 2 to 3, 2 to 4. Again, these are all absorptions, and then these are all emissions. So let's do an example. Calculate the energy of a photon of light emitted from a hydrogen atom when an electron falls from the 5th level to the 2nd level. So what we know is that the initial level is 5 and the final level is 2. So we can use our equation that we saw on the previous page. So delta E, which is what we're looking for, the change in energy is negative RH, 1 over, so in final is 2, so this would be 2 squared or 4, and 1 over n squared final, or I'm sorry, initial 5, so of course that's 25. So 1 over 4, I would just get the calculator out, so it's going to be equal to negative RH, and it's going to be 1 over 4. 1 divided by 4 is 0.25. 1 divided by 25 is 0.04. I'm keeping 3 sig figs because I'll use RH to 3 sig figs. So what's this equal to? So it's just going to be equal to negative RH times 0.210. Right? So it looks much more complicated than it is, because really we're only going to be using whole numbers, and we're not going to be using huge numbers. We'll really probably be using, you know, 1 to 6 or 7 at the most. So this shouldn't be too hard to solve. So we've got that value, multiply it by RH. So yeah, this is just showing it again. Now it's negative RH, so negative 2.18 times 10 to the minus 18 times 0.210 gives us the energy, which is negative 4.58 times 10 to the minus 19 joules. And of course, the negative is still there because this number was positive. The whole number is negative, and it makes sense because electrons are being, or energy is being emitted when it falls from a high level to a low level. So we expect that negative number. So it's not really negative energy, it's just energy that's being given out rather than being absorbed. So that's how much energy. So that's what I just said. Okay, and now that we know the energy, we can find the frequency, because we see right here energy is equal to h nu, and we can also find the wavelength. So I think I do that on the next slide. So we know the energy and the we know